is to find their total mass and divide by the mass of just one object. Now, in order to get a more accurate weight, some of you put a piece of rice, single grain of rice on the balance. Did that tell you a whole lot? No. You put it on the balance and the balance didn't change, or kind of wibbly and wobbly. So instead of just putting one piece of rice on there, you could have counted out 10 or 20 or 30 pieces of rice and found the average. This average mass is better to help you determine the number of objects than just the mass of one of them. Now, some of you looked on this other page and said, oh, it's got the answer for me. I'm not going to weigh it. I'm going to use somebody else's data. And so you've got a very interesting answer. Some of you weighed it yourself and show you should have gotten a more precise answer. Okay? Now, this works perfectly, especially if the variation in the size is slight. It's a very small variation. Now, let's take this to the next level. What if we wanted to know the number of particles inside this container? Counting it, would it be a good idea? Yeah, if you had a few lifetimes, you might be able to get to the end of just counting it. Counting it. There are lots of particles because these particles are very, very small in this sample. Now, chemists deal with particles that are very small. So they use mass, we use mass when measuring chemical compounds because it is not possible to measure them or count them directly. If I had this here and I wanted to count them directly, it would actually be impossible for me to count them. It would take more than a couple lifetimes for me to count each particle individual. This happens to be sodium chloride. To count each particle of sodium chloride, again, there would be a lot of counting to be done. If you counted one per second, you would not finish in your lifetime or in the next lifetime. It takes a very long time to do that. Since it is not possible to do this, a chemist will just weigh the sample and find how much you have of the sample. When chemists take measurements, they also determine what's called the percent error. The percent error is your observed value, what you observed, minus the actual value. You take the absolute value of those two, divide by the actual. Thing to think about is, were there really 326 items in there? Okay, these were built a long time ago, and if somebody cheated by opening the bag, could they have taken... Ideas we have. Yes, sir, Connor?
242.
You think 242. All right. So let's write that down here. 242. How many people agree with 242? You think 241. Why do you think 241?
Because he rounded up.
He rounded up. All right, so you only think there's 241. How many agree with 241? All right. So it's either 241 or 242, depending on how you round. Okay? And there's some debate on that. However, you can see that you have a number of raisins in your sandwich bag. Now, the cool thing about this is you could tell me how many carbohydrates are in 242 raisins. What would you need to know to tell me how many carbohydrates are in 242 raisins? The amount in one. You just need that proportion, and you could keep going, right? So we could easily determine that. If we knew how much volume a raisin took up, we could determine the volume. What size bag do you need for this? Do you need a Ziploc quart? Do you need a little snack bag? Do you need a gallon bag? All right? So there's all sorts of great fun things we can do with this, but you were able to calculate the number of small objects in a sample of many small objects. So at this time we have a short little video break. At this time I'd like to start the following video. See if I can get it to work. Stopped. See if I can get it to work here.
I've been assigned to welcome you to the Ministry of Defense. I have a letter from my director personally thanking you for these signs.
The new and probably most important word in the last little video clip. Ready, set, go.
Whoa!
Now, on the video clip you saw, what were they focusing the camera on? The mole. Now, the mole is a unique word, and the cool thing about the mole and why I showed you that video is because the mole has many different meanings. When you're looking at someone's face and they've got a big mole on it, especially if it's hairy, it's called a hairy mole. But a mole is not always something on someone's face or on their body. It's perfectly natural. A mole, Austin Powers in this video said he wanted to chop it up and make some what? Guacamole. What is guacamole made out of? Avocados. The interesting thing about guacamole is it's made out of avocados. Sorry. Now, the cool thing about the word the mole is chemists had a big problem. Someone would say, well, I've got some of this. Well, I got some of that. What if we take some of this and put them together? Well, how much do you want to add? I don't know. A lot of this. Well, what about this? I want a lot of that. Well, how many of these are in here? Well, there's a lot. What about these? Well, there's a lot in here. The problem was the chemist was trying to determine how many particles were in here, and all he could say was there's a lot of them. How do we keep track of them? How do we count them? From our last activity, we saw we could count small particles by doing what? Measuring their what? Measuring their weight or mass. So these containers here all have a particular mass of substance in them. This one is sodium chloride, this is copper chloride. Do they look the same? Do these two containers look the same? No. Do these look the same? No. All these containers look slightly different. They have different formulas in them, they have different volumes, they have different colors possibly, but there's one thing that's the same about all of these containers. Each and every one of these containers contains the exact same number of particles. In the last activity you did, same number of particles. Did they occupy the same volume? No. No. Did they look the same? No. Did they have the same mass? No, but one thing that was the same is they had the same number of particles. In chemistry, the word that is used to describe this amount is called the mole. Now, the interesting thing is, the mole was invented by a chemist with the last name Avogadro. Kind of like avocado. The mole is a specific amount of particles, and Avogadro's number is the number of particles in one mole. Now, inside this container, this happens to be a mole of sodium chloride. Inside this container, there are exactly, or approximately, I should say, 602 sextillion particles of sodium chloride in there. That's right. 602 what? Sextillion. Sextillion. That's right. I said 602. Sextillion. 602 sextillion. A sextillion is quite a big number. So another way of writing this is to use scientific notation. 6.02 times 10 to the 23rd particles are in 1 mole. So 6.02 times 10 to the 23rd particles is equal to 1 mole. This here is one thing you may have seen last night with working with big and small numbers. This is what is called Avogadro's number. This is equal to a mole is equal to this, and this is equal to Avogadro's number, and 602 sextillion. All of these are equal to one another. So if I said 1 mole of substance, how many particles would be in this container? 602 sextillion. If we use scientific notation, how many particles would be in this container? This is 1 mole. This is 1 mole. This is 1 mole. What if I had a mole of this and a mole of this? I'd have how many moles? 2 moles. There would be exactly 2 times 6.02 times 10 to the 23rd particles inside of both of these containers together. Now, would the particles be the same thing in this case? No. In this case, I've got sodium carbonate and sodium chloride. If you look at the formulas here, are these formulas the same? No. Sodium chloride has 2 atoms per formula. Sodium carbonate has 2, 3, 4, 5, 6. Even even though they both have the same number of particles, do they both have the same number of atoms? The number of particles, but do they have the same number of atoms? No, because a particle in this case is NaCl, a particle in this case is Na2CO3. So this one would have more atoms, this one would have less atoms, but they have the same number of what? Particles. A particle can be many different things. A particle could be a helium atom. That's a particle. A particle could be an oxygen, O2. A particle could be an NaCl. That's also described as a particle. Or copper sulfate, copper 2 sulfate. That's a particle. If you look at these, if you have one particle here, you have one atom. How many atoms do you have here if you've got one particle? Two. How many here? Two. How many here? 4, 5, 6. So you just count from the formula. So this is what is called a ratio between particles and atoms for each of these different substances. From the formula, you can tell that ratio. Now, the cool thing about the mole is we know, well, we're not going to count the individual atoms, we're going to weigh them. Moles are also little animals, just so you know. Moles are on people's faces. This is a mole in one. This here are 4 different samples of metals. All 4 of these samples of metals are equal to 1 mole. Which one would you say has the greatest volume? I. Which one would be the most dense out of these 4? Iron. Probably. But do they all have the same mass? No, not necessarily. So you would have to look at the mass. Where do we get the mass of these different elements? One way is to weigh them. And people have weighed them already and gotten what's called the average atomic mass. The average atomic mass is on what table? The periodic table. So what we can do is we can compare moles of something versus grams of something. So if we're trying to compare moles versus grams, which would be more toxic? 1 mole of arsenic or 10 grams of arsenic? In order to figure out how they compare, can we compare something that's in moles and something that's in grams? No, they're on the same units. So we would have to convert grams into moles, and then we could compare them quite easily. So we're going to look at the relationship between mass and moles first of all. We know a mole is 602 sextillion. Last night you looked at large and small numbers. Scientific notation, if it's got a positive number, it's a big number, bigger than 1. If it's got a negative exponent, it's smaller than 1. We move the decimal to the left, move it to the right. This is a little review. You've done this before for large and small numbers. The mass of 1 mole of a substance is called the molar mass. In our textbook, it's sometimes called the gram formula mass, or the gram atomic mass, or the gram molecular mass, or the molecular weight. All of those mean molar mass. I will only be using molar mass in here because it's very easy. You can say anything is molar mass and make it a little easier to focus. So I'll always be using molar mass. But if you see one of those other terms, it means molar mass. Now the relationship here